All right, recording is rolling. Welcome to another great day, Tuesday, August 15th. All right, so I'm going to wrap up the presentation, just have a couple slides. What did start out as a one-day presentation is now ballooned into something that could go on a few days. I'm going to wrap some stuff up real fast. And then I want to cover some basic foundational science stuff with you guys, scientific method, scientific notation, type stuff. We'll talk about the history of metric system units. Okay? I did have, let me pause this real fast. What's going on with, and resume. All right, we are back. All right, so there's an activity I've been wanting to do a couple days, but we're gonna have to bump that again. I think what I planned over last weekend was way too ambitious. We're gonna have to bump some activities. That's okay. We will make do. Gonna be all right, but in time. All right, so tomorrow's gonna be kind of a weird day. There are these class meetings going on. So first period is ninth grade, second period is 10th, third period is 11th, fourth period is 12th. We're gonna have classes in the auditorium. Right, so I have mostly 11th graders. So just for context, I'm gonna take my entire third period class to the auditorium. We're gonna do their off class period. I have some 10th and some 12th. Some of you guys are here, I know there's a mix. Those students individually would go down, right, so that everybody's gonna be in the auditorium at some point. And some of you guys might be down there two, maybe three times during the day tomorrow. Right. For that reason, I was trying to come up with activities that would be worth your time if you are here in class, but again, I'm going to be visiting the whole class tomorrow and a bunch of students. So if you aren't in here because you're in the auditorium, that you won't get too far behind and my classes aren't going to get super unaligned. I have some ideas. I'll see if I come up with better ideas tonight and we'll do this. I do need to bump all the trigonometry stuff definitely to next week. Really important foundational to this class. I mean, there's so much stuff I want to tell you guys. It's just going to take time, but that's okay. We're going to live between now and December. We'll get everything straight. And so this activity, we're going to bump to next week because this Thursday and Friday, I really want to do this Geneva Drive activity with the guys. I'm going to tell you guys index paper, glue. We're going to make some moving mechanical parts and some stuff I want you guys to get out of that. So lots of fun stuff, but in time. So for now, switch my screen over, share screen, the screen here. All right, let's hit these last few slides. All right, so materials for this class, have some kind of calculator is good. If you want the calculator, I've got a TI-30X2S on every single desk, and it's also the one that I use as I'm going along. So if you want to hit like exactly the same buttons that I'm hitting in the same program, blah, 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 okay. That calculator is a scientific calculator. It's about $10 or $15. It's really my favorite model calculator. Now, if you have something fancier, suppose you have like a TI-89 titanium plus to the moon, are you allowed to use that on the AP exam? Yeah, you can use that. As long as it doesn't connect to the internet, you can use that, right? If you want to use it in a class, that's great too. Again, I just use the scientifics, but whatever you're familiar with is fine. Right? I've been making a big deal about using your planner. I really hope that you guys have been making use of those, either have been for years or maybe just like starting yesterday. But please at least try it out for the next few weeks and hopefully see how much that helps organize your life and you can do lots of awesome stuff. Something to keep notes in for this class. Here, let me flip to next slide and I'll flip back here. Right, so this learning pyramid, the different ways to learn, right? So top to bottom, top's like more passive learning. As you go down, you get more and more active learning, right? So if you just sit here and listen to me talk, yeah, you maybe remember about 5%. I don't know if these numbers are 100% scientific, but there's like truth embedded in this slide here, right? If you read something that's a bit more active, you're going to learn a little bit more. If you write notes, that's a bit more active, right? You're going to learn more. Your brain makes neural connections as you're writing stuff down, where you see it, it might make sense. Oh yeah, that checks out. But put a blank paper in front of you and say, okay, well, solve it now. And if you've done it by hand, then your brain's able to pick it up, say, oh yeah, and take you through the motor motions. You can actually solve the problem. Versus, if you're trying to solve something for the first time, say, well, I saw it. It makes sense when I saw it, but now that I've got the pencil in my hand, right? So stuff to figure out, right? So please do make a good habit of trying to keep notes in this class in general. I know the last few days have been like really introductory, like fire drill stuff, so it's not a good opportunity for notes. But it's in there today, maybe a couple things, right? I know sometimes I take notes and I look at my notes at the end of the day and I wrote stuff that I didn't even remember writing. It's like, oh, I wrote that. And it's like, oh, well, good thing. Otherwise I wouldn't remember. The best way you can ever learn something is to teach others. Like this class, I got really good at physics in part by, say, I tutored at university and just like teaching this class so many years, right? Just like learned it back and forth. No, you guys gone through it the first time. You're seeing a lot of these concepts the first time, right? But a lot of days I'll have you guys in small groups. Like today, again, not quite gonna get to the activity I wanted to, but you guys are gonna have lots of lab opportunities. And if you guys are helping each other out, asking genuine questions and helping each other out, that's like the best way you can learn anything. Oh yeah, back to here. AP students, lab notebook. Okay, so here's the deal with this. AP, one of their rules for the program is you're supposed to keep a lab notebook. If you want to have a composition book like this and keep all your labs in it, then that's a good idea. Last year, I had a handful of students who did that. They had a notebook, looks like that, and they turned that in for all their labs, and they graded them like that. What might be more convenient is just to have individual papers of labs, so you turn those in, and then I give them back to you, and you collect your own lab book together, right? You just assemble all the labs individually, make your own notebook. I've been told, I don't know how often this is really enforced, that suppose you pass this class, the AP exam, pass the AP exam, like you get a 4, great, looking solid, go to a 4-year university. They say, oh yeah, you got a 4 on the AP exam. They almost always give you credit for the class, right? Maybe you want to retake it, get a different perspective, see things second time, or maybe you just want to like move on, right? So how physics works in college is usually there's a 3-credit class, like a normal class, but there's also an additional 1-credit lab class, right? So it's like 4, right? 3 for the class plus a lab. And I've been told that universities want to see your high school AP lab notebook to get credit for that extra lab class. Again, I don't know how often that's enforced, but supposedly that's a possibility. So keep all your labs, right? We're going to do lots of labs through this class, and they're going to have for reference anyway. You can look back and see, oh yeah, that's right. That's how we did like derive this or that equations. Yeah. Right. All right. You guys got some note cards on your desk. Okay, so here's an optional activity. If you write your name on it, just a few facts about yourself, and then turn that in, and I'll probably read these a couple times and learn some things about you guys. Traditionally, some things students might write are things like, so I was born in such a, I was born in Italy and I enjoy soccer and I want to be an aerospace engineer. I don't know, just make something up. So this appeals to you, you want to share something about yourself, then I'll read these later. And if not, you don't have to. Right? So everybody see this gray tray? Gray tray. You guys see gray tray? It's a gray tray. Ooh, it rhymes. Gray tray. Anything turn to this gray tray, I will eventually get from you guys. Any assignments you turn in. So if you pop that note card in the gray tray by end of class, then I will alphabetize those and learn some stuff about you guys. All right. So again, this presentation goes on way too long. Got mechanical bearing system. Got lots of demo stuff. But yeah, let's just go ahead and wrap this up here. So let me flip my screen back. All right. I think we are back now. We're back. All right. So let me take you guys as far as I can through this basic science stuff. Tell you guys a little bit of history, measurement, units, the whole deal. Okay, so here we go. I'll start with this right here, scientific method. So I told you guys the whole story about for thousands of years, people are running around trying to make sense of the world, like living and breathing with the earth. At some point, then agriculture and then writing and start to think abstractly and then start to come up with systems of thought, right? At some point, there was early Greek science, then along comes the Dark Ages, and by the time Renaissance rolls around, people have philosophy and logic, but by the end of the Renaissance, along comes Galileo, runs up Leaning Tower, starts dropping different stuff off, freaks everybody out, because he's coming up with a new method of approaching things to answer questions. This right here, scientific method. Different textbooks have slightly different versions of this. You might see 5 or 7 steps, but I guess this is like a different version of this, right? So normally you start off with some kind of question or problem. I might ask you guys this. I'm trying to move along a little faster, get as much as I can in the class period. Hopefully a lot of stuff is review time for you guys. Maybe learn a few things here or there today. So you start off with some kind of question you want to answer, some kind of problem. Okay. A lot of textbooks have as a second step some kind of background research. Maybe other people have already addressed this problem. You can see what conclusions they came to, maybe what their methodology was, maybe what was their approach, what were certain considerations they have. I didn't even consider like the temperature of the room might be a variable. Wow, didn't even think about that, right? Something like that, right? Right. So now you got your background research, kind of what's out there, right? Now you could formulate a hypothesis. Who could tell me what is a good, like in a nutshell, definition of a hypothesis? What is that? educated guess. Yeah, that's a really common definition, see, right? Like an educated guess, right? So if you're guessing how something works, now if you can put it in like an if-then statement, that's usually pretty strong. Like, see, if I change this variable like this, I think this other variable will do this, right? If you can come up with some kind of um, relationship prediction, like, I predict like an inverse relationship. If I increase the mass, I think the acceleration will decrease or something, right? If you can quantify it, even better. When Einstein came up with the general theory of relativity, it started off as just like theoretical physics on paper, right? But he was able to make a hypothesis, like very precisely. He says, like, oh, if you look up at the solar eclipse, then the stars in the sky are going to be shifted a little bit from gravitational lensing. I predict exactly how much, and it was very like specific hypothesis, right? So hypothesis, which is a correct scientific hypothesis? Okay. So we got a couple options. Let's see, show hands. Is a correct scientific hypothesis one that you can only ever verify, or one that you can only ever falsify? Correct scientific hypothesis, something you can only ever verify, something you can only ever falsify. Show hands. How many guys think a correct scientific hypothesis you can only ever verify it? Only ever verify, right? Who says falsify? Falsify. Oh, all right. What am I even teaching this class for? You guys got it. Every guy, right? Falsify. Now, what do you mean by that? So, in science, really scientific thinking, there's really, this is kind of weird, but it makes sense, right? Sit down, think about this. You never really prove anything. All you can do is like disprove alternatives, or like trying to figure out how does something work. You say, well, maybe there's like 10 possibilities, and we disprove these 9, and we can't imagine anything else. Just limitations of our imagination. So all the theories point to must be this other thing, right? How our brains are wired is to be more like a lawyer than a scientist, and the scientific thinking is something that you have to be trained in. I mean, that's why you guys are in school. I sit right here to be thinking about these kind of things, right? So how our brains want to operate is that, okay, you have some idea of how X, Y, or Z works, and your brain seeks out evidence to prove that that would be true. Now that is actually a cognitive bias called confirmation bias. Confirmation bias, right? And all of us have Homo sapien brains. All of our brains work like that, right? I think this or that works this way, and then you look for evidence, like, oh yeah, I'm totally right, of course, because look at that evidence right there, right? And then lots of people all say the same thing, and everybody disagrees about things, and it's like, well, hold on, that's like a lawyer way of thinking about things, right? Like you're crafting a story. Right? In science, though, you're trying to poke holes in your hypothesis. You're like, okay, I think that's how this works. But if this is really a true, strong hypothesis, if this is really correct, then can I come at it at every angle that I can possibly imagine, or other people could critique it and peer review it and try to poke holes in it? If nobody can, and there's a really good possibility that it's true, right? Especially if there's no alternative hypotheses floating around, right? So maybe a classic example is you work at a pharmaceutical company and you come up with some drug for some ailment. Okay? I think this drug will cure this ailment, right? So kind of confirmation bias way of handling this is you give the patient the drug, they get cured, you're like, oh, well, that works, right? But come back to science, say, well, hold on a minute, were they cured because of the drug, or maybe it was just a matter of time to heal, or was it even placebo effect, right? Placebo effect. Sometimes you just give someone a sugar pill or just like a shot of water or something, right? And their brain takes over and heals them. It's crazy that happens, but right? So now you really have to test this drug against the placebo, right? So you're trying to poke holes in this idea that this drug even works. Right? How does the drug do not against not having drug, but against against the placebo, right? Something like that, right? So yeah, falsifiable hypothesis is a scientific way to think that. All right, so now we're rolling over to experiment. Here's the heart of the scientific method. Okay. Now maybe there's lots of variables going on with lots of phenomenon all the time, and you set up some experiment. Now independent variable, that's the variable that you intentionally change, right? I want to change the mass of this object, for example, right? See how does that affect blah, 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 right? Maybe you have some like dependent variable that changes because you change the independent variable, possibly, and unless maybe there's no relationship between the two, in which case there would be no change in the dependent variable, right? Now, ideally, if you can, in a well-controlled scientific experiment, you want how many independent variables, how many things that you're changing at a time? One if you can, right? Sometimes it's difficult to set up a situation where you can, but in this class, for the most part, you can, right? So I'm going to leave everything else controlled, right? Like your controls are things that you don't change, right? So I'm not going to change the gravity field of the room. I'm not going to change maybe the temperature of the room, who knows, practically, right? If I'm changing out the mass, maybe I leave the distance that something is the same, right? Right. So, right. So one thing you're changing, independent variable, you leave everything else controlled, ideally, right? And then there might be one or maybe possibly more than one, dependent variable for there's like something that's changing. Right? In the real world, and for other subjects too, sometimes it's hard to craft something like that, and you need to have, say, a more complex system, or you might have to set up something like what's called a natural experiment, right? So, a couple examples, maybe something like climate change. Well, what would the world look like, say, if we weren't burning fossil fuels versus if we are? Hard to set up a really well-controlled experiment because we only have one planet and one timeline. See if you could split like parallel timelines. You can set up like, oh, we got like 50 planets here and 50 planets here, right? But, okay, we only got one, right? If you work in economics is a branch of science, right? But we're working with like natural experiments in the real world. What happens if you institute a policy like, hey, let's increase the minimum wage? What effect is that going to have down the road? Well, there are tons of variables going on in an economy, so it's not like single thing happening at a time, right? So it's kind of hard to work in isolation. So you have to say, well, what does this state look like versus this state, and then control for all these other like 10 other variables, and there's like a whole process. So that can get pretty messy. There's ways to sort of tease your way through the data like that. But in this particular class, usually it's pretty straightforward, right? Have one variable, you change an independent variable, leave a bunch of stuff control. Right? You have like a dependent variable. Right? Analysis. So the analysis in this class is mostly going to be graphical relationships. So you have the guys plot x-axis, y-axis, put variable here, and then see, put a bunch of dots for whatever you measure. See, I run this stopwatch, this much time, I want this distance, right? And then see what kind of relationship you get. Maybe you'll get no relationship, maybe you'll get a linear relationship, maybe you get like something looks like a parabola type shape. There's a handful of common graphical shapes you see, and if we don't get to them today, it's one of the slides coming up. Okay? And then finally from that, come up with some kind of conclusion. I should say too, tying these two together. If you get something like a parabola shape, how do you come up with an equation for a parabola? That's a curvy type shape, right? I'm going to show you guys a trick that AP loves to use, which is linearization. So you can actually manipulate the axes and pull everything out to a straight line, which is much easier to craft an equation for. Right? And a really common type conclusion could be some kind of equation or some kind of formula, right? Like a bunch of formulas on these posters hanging around the room right now. They are conclusions from experiments that have been done over the last few hundred years, right? So there you go. There's a scientific method in a nutshell. Hopefully that's a good refresher, and maybe you learn a couple things, right? All right. Systems of measurement. All right. Okay, so talk about the SI system, System International, International System of Units, aka the metric system. We're going to start with these three, and then we'll expand from here. So I'll give you guys a little history. If you go back hundreds of years ago, say like the Middle Ages, every locality had their own system of measurements. And what did they use for a system of measurements? Well, just usually what was applicable in their everyday lives. So like the width of your hand, like a palm was a common unit of measurement, maybe like a foot, right? How much land area can you farm in a day? Let's call that an acre, right? I mean, most people were farmers, so that makes sense to be a unit, right? Like 1,000 paces became a mile, right? But there's some problems with that. One is, once you start getting all these units together in different ways of measuring them, now you start to get like weird conversions between one and the other, like 16 ounces in a pound or 5,280 feet in a mile, right? So these weird like conversion factors you have to memorize, right? Also, if you go from one locality to another locality, right? People got like different hand sizes or different definitions of like what is a pound, right? Maybe you can kind of try to standardize it. Well, let's use the King's foot, but then okay, now the French foot and the English foot is like two different lengths, and now if you're trying to like communicate information, say like locality to locality or somewhere or country to country, you can't, because what do these measurements even mean? Right? So nobody's on the same standard, right? I mean, it kind of makes sense if you're back in the year 1200. There's no interchangeable parts. There's no manufacturing system to create like this precise ruler that's exactly so many centimeters long, right? So everybody's just got like their hands and their feet to work with, right? So where and when does ultimately this metric system come about? Who knows? Where and when does the metric system come from? Let's start with where. What country? Okay, not too far away. France, yeah, winner, France. All right, you guys got this. Yeah. And about what time period do you think we're talking about? Through kind of a ballpark year up here on. Okay.
Late 18th century.
Aha, there you go. All right, good call. Late 18th century. Hey, what was going on in France in the 1790s?
Revolution.
Revolution, French Revolution, right? So a little backstory about 1780s. The economy of France was really bad. People were starving, terrible. The French government had helped us, the United States, win independence against Britain, and all of the French people were looking at our system of government. So wait, if they get a republic, they get to like elect their own leaders. Oh man, well, I hate like starving over here. Things got very choppy, and while they were reforming their government and whatnot, they say, hey, you know what? Let's also reform a bunch of other things. This is Age of Enlightenment. Let's reform this system of units. Right? Let's come up with things that can be universal. So let's find measurements that, like, no matter what locality you are on the planet, you have access to the same resources to come up with the same units. Was the thought process. Okay. All these conversions, they went with like base 10 conversions. So we'll get to prefixes, but so nothing to do with like 5,280 feet in a mile. Now everything's going to be scaled up by 1,000, right? So like 1,000 meters a kilometer, boom, right? 10 to the 3. Right. So I'll start with this one here. What was the original definition of a meter? So, oh, that's broken. Okay. So meter stick right here. Right. So this meter stick, about 3.28 of these floor tiles, right? This meter stick. Right. Where did this distance come from? Well, they said, hey, let's no matter where you are on the planet, you're on the planet. So let's go from the North Pole down to the equator, around the curvature, divvy that into 10 million parts, and boom, that's where this comes from. Now that's the original definition. Now over time, the definition has changed, but it's just been equivalent to that pretty much, right? Plus minus a tiny bit. Okay? So that's the starting point of that. If you take this 10 centimeters right here, you guys see 10 centimeters? You make a box. Let's go 10 centimeters by 10 centimeters by 10 centimeters. Okay, you fill that with water. That has a mass of 1 kilogram. So that's the original definition of a kilogram. Or if you like, if you do 1 centimeter by 1 centimeter by 1 centimeter, 1 by 1 by 1, you fill that with water. That's a gram, right? There was a debate at the time, should kilogram or gram be the base unit for mass? If you come from chemistry, you probably work with grams, probably, right? But they ultimately with kilogram is the base unit for mass. So just take that to heart for this class. Okay. And that ends up being important because later on we're going to start combining these units and make composite units. And this is like an ingredient that's baked into the cake for composite units. Give you guys an example. There's a difference between mass and weight, right? Mass is like the amount of matter, the amount of inertia something has, and weight is like a gravity force, like the Earth pulling down. I can feel the Earth pulling down on this. Right? Now, the U.S. customary units that we got from England don't have a very good distinction. They just call everything pounds, pounds mass, pounds force. Like, but the metric system, they do a really good job of saying, okay, these are totally different concepts or totally different units. Okay? And what is weight and force? Like as a force, weight's a kind of force, right? I can feel the Earth pulling down on this. Right? Well, I can measure that in newtons. And what is 1 newton? Kind of like pounds, but it's a different deal. Oh yeah, go ahead. Squared. Yeah. Kilogram meter per second squared. All right. So that doesn't make any sense right now. That's okay. But as time goes on in the semester, that'll eventually make sense, right? As we start to apply formulas and you look at how the units carry over. Yeah. 1 kilogram meter per second squared. Yeah, is 1 newton. So that's a unit of force. Right? Yeah. Good thought. Right. Let's go with this too. Yeah. So see how like kilograms like baked into the cake of what 1 newton is equal to, right? So let's try that. Okay. Let's say about this. Right. Second. So 1 second is exactly what you think it is, right? You look at the clock, you see the second hand ticking, right? 1 second per second, right? So taking our day, divvy that into 24 hours, each hour into 60 minutes, each minute into 60 seconds, boom, you got a second. Right? Now, the French at the time, back in the 1790s, were trying to say the French government was trying to standardize everything according to these base 10 scaling up and down. And they tried to do that with time too. It didn't stick. But so they're trying to do with time. Say, hey, what if we had like 10 hours in a day and 100 minutes in an hour and 100 seconds in a minute? And so that was standard for, I think, like a few years in France, but it didn't stick around. It was just like too weird for people to get used to. Right? So we use this one stuck around. So what a second is. Right? 60. Where does 60 come from? Why 60? Why are there 60 seconds in a minute? Right. So I don't think anybody exactly knows the answer to that, but there's some good speculation. So I'll give you the best guess that people have. And it goes like this. That's what?
10 fingers, 6 times.
Huh. Yeah, like multiples of 10 or 9. Yeah, I've heard this theory of like why use big 10 system has possibly something to do with like how many fingers we have. That's a good possibility, right? That's gonna be the case, right? If you look at different place value systems around the world, right? Here, let's go back before that, right? Look at Roman numerals. Roman numerals are not a place value system, right? You can count, but if you start counting too high, it's like crazy numbers. You can't really do higher level math with Roman numerals, right? You need some kind of decimals, some kind of place value system. And different cultures around the world have developed different place value systems. Base 8's been popular, base 12, base 16 in China was popular for a long time. And then you guys know we're using base 10, right? So we have 0 through 9 and then it rolls over. Okay? In Mesopotamia, they were using a base 60 system. So they had characters 0 through 59 and then would roll over like that. So they had a place value system, it was just base 60. Wonder if that's related to this, right? You guys know like 360 degrees in a circle? Where does that come from? There's probably a connection there too, right? What is cyclical that's also very close to 360? Days in a year, right? Days in a year, right? So 365, so it's like 360 plus a few, right? So again, this is kind of speculation, but it's probably where this comes from. It's like, okay, the calendar year is really close to 360 days. It's like degrees in a circle. Why aren't there 100 degrees in a circle? Again, probably goes back to Babylonia, right? Right, that's divisible by 60, right? 360 divided by 6 is 60, right? 60 degrees is really nice angle too to work with in terms of sine cosine. All right. Yeah, so that's stuck around, and again, it's probably why to this day we have like 60 seconds in a minute whole deal, right? Rather than something more like 10 or 100, which might seem more like in line with this thought process, right? So great, we got kilograms, meters, and seconds. These are really the only 3 base units that we're going to need for the entire first semester. This is going to take us all the way to Christmas right here, because you can combine these and make composite units. Speed, meters per second, kind of like miles per hour, meters per second. Acceleration, meters per second squared. Energy, measured in joules, kilogram, meter squared per second squared. Okay, so this is all we're going to need to measure anything we want to measure first semester. Okay. Now there are other things you can measure too. Ooh, actually, before I flip the slide, maybe I'll ask you guys, what do you think you could also possibly measure that's outside the scope of those 3 things? Right. Well, altogether, you may maybe come up with 7, arguably, that could cover like anything you can possibly want to measure. Okay, so cover these 3. Right? How about electric current, right? Or something to do with electricity, or maybe charge or something, right? Okay. So 1 amp, 1 ampere, 1 amp, same thing as 1 coulomb per second. It's like a rate flow of charge. I make this myself. I might have gone with coulombs for charge. But as long as you have one or the other, you can drive the other, right? Right. So some do with electricity. In the spring, we'll break out ammeters and voltmeters. You guys measure the things in a circuit. Okay. Ooh, how about temperature? Right, temperature. And we have different temperature systems. We got Celsius, Fahrenheit, and this one here, Kelvin. Okay. Why is Kelvin a better system than Celsius or Fahrenheit? Is this a what kind of system? Like an absolute system versus like relative? Like Celsius and Fahrenheit go negative, but it doesn't really mean there's like negative of something. It's just kind of like a relative scale. Okay. Do you guys ever work for? Oh yeah, go ahead.
Isn't Kelvin just Celsius but shifted like 273 degrees?
Exactly. Yeah, you're right. Kelvin scale is scaled exactly the same as Celsius. So a change in 1 degree Celsius, change in 1 Kelvin, or the same thing. The change is the same, right? Right, it's shifted like 273 degrees, right? So the coldest you can get in the Celsius scale is like negative 273 degrees Celsius. There's no such thing as negative 274 degrees Celsius, right? Did you guys ever work with the ideal gas law? Ideal gas law, maybe in chemistry, okay? Oh, okay. Looks like a bunch of guys have. So let's say you have a balloon. The balloon's tied up, right? And you heat up the balloon. Is that balloon going to expand? Okay. Yeah. Is the volume change going to be proportional to the temperature change? Yes, as long as you're working in an absolute scale, like Kelvin. Okay. Right. That would probably come back in like January, February. Okay. Ooh, how bright is that star in the sky? Ooh, was it always that bright? Is it going supernova? Is it blowing up? What's going on with that star? How can I quantify that? Ooh, I might need something like like candelas for luminosity to measure that. And if you're coming from chemistry, mole is just a really big number. So I don't know if that one even counts, but it's just like counting things, right? So you got so as far as we know, everything that we've ever wanted to measure, you can measure in terms of these base SI units. Again, you can combine these and make composite units. Now, remember I told you guys the original definitions of some of these things? Now, those definitions have changed over time. This kilogram, for example. You know what? Sorry, I think I missed this tiny detail. Let me go back and fill in some details here, right? Remember I was telling you guys the difference between mass and weight, right? Okay, let me compare a couple of objects. This guy's 100 grams. This guy's 1 kilogram, which is 10 times as much, right? So if I shake this back and forth, notice I'm not picking up the weight of this. Nothing to do with downward force pulled by gravity, right? But this guy is much easier to change the state of motion, right? Because this guy's a lot more material. This guy's a lot more massive, has more inertia. It's harder to change the state of motion. You get that, right? Right, you guys get that, right? And so that's a mass idea, inertia. Let me go ahead and pass this around so you guys can get your hands on this and really feel this, like how massive that is, how heavy that is, right? And just go ahead and pass that around. So the definitions of these have changed over time. So just to fill in a little bit of fun history here. For a long time, they were based on like physical objects. So you guys saw where the original definitions came from. But then what the French did was to create like physical rods that were like exactly 1 meter long. They just stored them in some warehouse in Paris. Right? They had like kilogram masses that were like the official kilograms. They were all identical. Right? At least they were at one time. Then what they did, here's like a weird part of the story, is other countries want to pick up the metric system, so they send around these rods and these kilogram masses around the world. Right? And then every few decades, they bring them back in for a weigh-in. So, oh, let's get one from Australia, one from Japan, one from Canada. And weirdly enough, the values of these things would actually deviate a little bit. So like 1 kilogram didn't stay 1 kilogram. Why? I mean, they took off all the dust. They said, well, what your fingerprints have some kind of oils on them? They got rid of that. It's like, oh, I don't know, maybe some kind of chemical reaction with the oxygen. Who knows? But these things aren't exactly stable. I mean, even a rod, the air conditioning goes out and the room warms up and this thing undergoes thermal expansion. And now the definition of the meters change, right? So more recently, what physicists have been able to do is to redefine all these units, not in terms of physical objects or even like properties of the earth or water, but instead in terms of universal constants that are unchanging. For example, the speed of light in a vacuum is this value right here. It's like about 3 × 10⁻⁸ meters per second. That is true no matter where in space you are, right? Here's the frequency that the cesium atom will vibrate with, right? And the reciprocal of that can tell you something about how much time has passed, right? So the modern definition of a meter is actually how far light travels in a tiny fraction of time, right? Which might seem kind of a weird abstract definition, but now it's something that could be defined in terms of universal constants and unchanging, right? And actually all those base units have been redefined in terms of these universal constants. Most recently, mass. It was a kind of a tricky one to complete with, but there you go. And some of these you guys are going to see throughout this class. You'll see the speed of light. You'll see universal gravity constant. Maybe elementary charge, although AP doesn't cover that, but in AP1 anyway. But yeah, okay. So you'll see some of those, but not all of them. All right, scientific notation. So you guys are familiar with this, right? Scientific notation. Okay, again, so hopefully this is just pretty good review. Some of the numbers that we're going to be working with are just extremely large or extremely small numbers, and there's better ways to write them for a number of reasons. Remind you guys why. Suppose you want to send a satellite around the planet. So we got to send a rocket up to the International Space Station. How fast do we have to get going? How fast is going to be orbital speed be? I bet that has something to do with the mass of the planet. But if the planet's more massive, you got to get it going faster, right? So if you want to solve it from scratch with these equations, you got to know the mass of the planet. Or vice versa. If you experimentally send something into orbit, then you could, you see like how fast it's going, you can calculate the mass of the planet if you know the orbital speed. Okay, so it goes back and forth. Anyway, so you might have some number like this, like the mass of the Earth. Great, I'm going to plug that in my equation so I can figure out how fast I have to get the rocket going. You're sitting here typing all these zeros, like, oh, dang it, I lost track of the zeros and my computer screen lost out of width. And right, so all these zeros, are they actually zeros anyway, or are they just placeholders? Right? Like, do we actually know that's a zero? What if it goes like 1508? Oh, who knows? These are just placeholders, aren't they? For some decimal place out here, right? There's only so much precision, goes to about here maybe, right? So there's an easier, like more convenient way to type it, which could be like this. Right? So the rule is you take your decimal place, roll it over to the units place, which would be like right here. Right? And then to restore the decimal place, say, okay, well, I need times 10, times 10, times 10. Well, how far did I move? I moved to 24 places. So I'd have to multiply by 10 24 times. That's 10 to the power of 24. Okay? Notice it does not say times 24. It says times 10 to the power of 24. It's 24 decimal places, like I said. Right now, another thing too, another reason scientific notation is really good is because it tells you, this scientific notation version tells you how much precision you have. Like the original, I probably need to redesign the slide, and I'll show you guys why. I'll point out why. Okay. Oh, you guys see 5972190 and then a string of zeros. Okay. This zero right here, is this zero significant? Like, do we know that that zero truly is a zero, right? Or maybe it's like a 3, right? Well, it's kind of hard to tell, right? Just look at the number. Maybe it's ambiguous the way it's written. But if you write in scientific notation, then you know for sure, because you would write like this: 5.97219. And if you stop right there, then the zero is just a placeholder. But if I wrote 190 after this two, which I should type the 19 at least. Okay. If I wrote 190, then having that zero there, like you took effort to write it, whereas you didn't have to. So you were communicating to whoever's reading it that yes, in fact, that zero, we have measured that level of precision. We know for sure that is a significant zero. Okay. So that has that advantage too. Okay, let's go smaller. Mass of a proton, tiny number of kilograms. Remember, kilograms is the base SI unit. Negative exponent. Guys, do negative exponents make numbers negative? No, they just make the numbers really what? Small, really small. So 10 to the negative 27, that's like dividing by 10 and doing that 27 times. Okay, right, so you guys can do that, right? You guys good on scientific notation? We type this real fast. 1.673 times 10 power of, open parenthesis, negative 27. Boom. All right, I gave you scientific notation anyway, but you guys get the idea, right? All right. I'm getting into prefixes, so here's a good lead in, right? So here's 1,000 dots on the page. Kilo is 1,000 of something. Milli is 1,000, right? Like, for example, kilogram is 1,000 grams, or millimeter is 1,000th of a meter, right? Look on the meter stick. Okay. So this whole stick is 1 meter long, right? But there's these tiny lines you just see from one to the other. So it's like 1,000th of a meter stick, right? There's 1,000 little tiny tick marks on that 1 meter stick. Right. Let's get a wider view of this. I have a couple of slides for prefixes, right? There's these that are hanging out pretty close to the base value, go from 1,000 to 1,000, and then there's like really small and really big. Okay, so start with this one right here. We'll use some of these, right? We'll use centi, like for centimeter, you'll see a bit, right? And then milli and kilo, you'll see quite a bit, right? Some of these other ones show up too, like decade. Oh, hey, look, the prefix decade, 10. Do you guys ever learn a mnemonic device for these prefixes? How does it go? Maybe somebody knows this.
Like King Henry drinks something chocolate milk.
Died by drinking chocolate.
Yeah.
Okay, there you go. Yeah. King Henry died by drinking chocolate milk. You guys are saying, right? All right. Yeah, that's what students have been telling me all day too. I always heard contaminated milk, although maybe chocolate milk will kill you too. In 6th grade, I was told kittens hate dogs because dogs can't meow. What's that? Let's look at these. Let's go really small and really big. Okay. So these are 1,000 at a time, right? 10 to 3, 10 to 6, 10 to 9. Right? So if you have 1,000 of something, here's kilo, right? Kilometer, kilogram. Mega is a million, that's 10 to the 6. Giga is a billion, 10 to the 9. Right? Hey, you guys work with computer files? You have 1,000 kilobytes, goes over to maybe like a megabyte, then 1,000 of those, now you have a gigabyte. Right? Now computer files, it's actually a factor of 1,024. It's a binary thing, but it's real close. Right? Let's go the other way. Let's get small. Milli, 1,000th of something, right? Millimeter, right? Milligram. If you're micrometer, right now you're a millionth of a meter. Right? Micrometer could be a millionth of a meter. Right? Go another step. Nano. You guys ever heard of like nanotechnology, nanobots, talking about order of magnitude of like the billionth of a meter. Woo, yeah, real small there. We're going to be familiar with those, see them more organically. But if you see something out in the wild, like giga something, you're like, oh, okay, like gigahertz. Okay, I know that's a billion hertz, right? Dimensional analysis. All right, let's do this way. This is a unit conversion version of dimensional analysis. I don't know, maybe I need to change this title because there's a bit more broader perspective of stuff you can do with dimensional analysis. I want to take you guys through too, but let's do a basic unit conversion. You guys done unit conversion in chemistry probably all the time? Okay. Let's set up some railroad tracks. Okay. Railroad tracks. How are we doing here? 7. If you've got some paper in front of you, then you can try this out too. Okay. So the question is, you have $1 billion, you spend $1 every second. How long to spend all the money? Ooh, first order of magnitude. Is this going to be some number of hours, some number of years? What do you guys think? Maybe months, right? Maybe, right? Let's try it out. So I'm going to start with my given value, $1 billion. Right? Ooh, I didn't give myself very much space here. Hey, let's take a page from scientific notation, like orders of magnitude. A billion, guys, a billion is 10 to the power what? 9, good call, 10 to the 9. Oh, and I need a unit because in this class, very rarely do you ever see naked numbers. Right? These numbers have units attached to them. We're talking about dollars, throwing a dollar right here, right? $1 billion, boom, 10 to the 9. Okay. I'm spending $1 every second. Okay. Now the way I'm going to interpret this is I'm going to say $1 is equivalent to 1 second, right? Like money equals time, right? So I'm going to do something like this: $1, 1 second, right? Okay. Now the way I've written that is like 1 second per $1, right? That right there is a fraction, right? And I'm taking one value and dividing by something that is equivalent, right? Since you guys have been through chemistry, I know it's been a few months, so give you guys a refresher, but you might remember something like if you're converting feet to miles, you might say 5,280 feet and 1 mile. But since those are equivalent distances, if you divide something by itself, it's just always equal to 1, right? Try to remind you guys what the theory is behind why this works, right? So if you take some original value and you just multiply by 1, you're not actually changing it. What you are doing is you're swapping out the units, right? In this case, I set this up in such a way that the dollars cancels. And now at this point in the process, I know it's going to take me a billion seconds to spend all this cash, right? All right, so let's go on. Let's go, how about seconds to minutes? How many? 60? Does the 60 go on the top or the bottom? How many of you guys say the top? How many of you guys say the bottom? All right, most of you guys say the bottom. Awesome, awesome. Right? How'd you guys know it was the bottom? You're setting it up so that the unit cancels out. Right? See, if you put it on the top, you have square seconds per minute. Right? But the way it's up here, oh, look, seconds cancels. Right? Now we know how many minutes it's going to take to spend all the money. Right? Let's go another step. 60 minutes in an hour. Right? Does 60 go on the bottom again? Yep, 60 minutes is equivalent to 1 hour. Right? Throw a little 1 here, right? Okay. But now it's set up in such a way that now we know how many hours to spend all the money. Okay? Let's go 24 hours and 1 day. Right? Again, those are equivalent. That fraction is still equal to 1. Right? But now hours goes away. Now we know how many days. Let's just cut straight to years. It's going to be some number of years. Right? Can I go 365 days, 1 year? Right? Now, if you want to go 365.25, you can get some more precision, but that's not going to really change the answer that much. Right? So now I know how many years it's going to take to spend the money. Calculator time, multiply across the top, divide all the stuff down here. Let's try this out. Open parenthesis, 10 to the power 9, close parenthesis, divided by. The way I'm going to do it, now I've hit divide. I'm going to open up a parenthesis and multiply all this stuff together. Right? So it's all grouped together in the denominator. 60 by 60 by 24 by 365. I'm getting 31.7, and the unit is years. So there you go. Right? Another context, when you are 31 years old, you can say, I'm a billion years old. Oh yeah, a billion. Got another example for if you calculated like the orbital period of a planet and you want to put it in like Earth time, you can do that. So got a couple there. Right? Scaling. Scaling. So AP loves to ask questions of like you scale it the size of a planet and like what happens to the surface gravity, for example, is a classic question, right? And you have to think about if you scale it the size of a planet, what different properties are changing in what ways. So let's start with a cube shape, right? You guys see this little tiny box down here? Let's say you blow it up by a factor of 3 in every linear dimension. Now we live in a 3 spatial dimensions universe, and that ends up being important for some of these questions, right? So you guys see this huge crate, right? Let's compare the little tiny box to the big crate, right? So say expanded by a factor of 3 along each dimension. So 3 times the width, 3 times the depth, 3 times the height, right? Also 3 times the perimeter. Anything that's in one dimension, right? So it's gonna be 3 to the power 1. It's just 3 times. Okay? What about a 2-dimensional concept? What if I paint the face of the? Oh man, you get as far as I wanted to, but that's all right. I'll see you guys tomorrow. Yeah, I'll wrap up those few slides there. Yeah, if you like, you can throw that card in the gray tray, and you guys have a great day.